Hi, I'm Erik Thostenson. I'm faculty in mechanical engineering and also material science and engineering. And I want to talk a little bit about some of the work we've done over the past couple of years in novel smart garments, specifically integrating sensors into wearable clothing. And it's using this novel technique that we've developed in my lab, specifically where we integrate nanomaterials. And this next slide this is kind of my signature slide because I like to start with this slide because I think it gives you a sense of the different levels of scale. And in this case, these are fibers where carbon nanotubes were grown on the fibers. So if you see this micrograph right here, this is actually a fiber, a microfiber that's about 7 microns in diameter, or about 1/10 the diameter of a human hair, and grown onto the surface of that are carbon nanotubes. And what these do is they create a nerve-like electrically conductive network on the surface of the fiber. And we've actually developed a novel technique where we can apply this to a wide range of both natural as well as synthetic fibers. So there's this, it's really the enabling technology is this what we call electrophoretic deposition. And what we do is we chemically functionalize these carbon nanotubes, and the chemical functionality allows them not only to disperse, but also where we can manipulate them with an electric field. So they get a positive charge, and when we disperse them in a solvent, and in this case we're using water, and we do this at room temperature, so it gives us a lot of opportunity to apply this to a lot of different fabrics. So on the left, you see this, kind of a cartoon, is that we have these carbon nanotubes that are functionalized with polyethyleneamine, and then we apply an electric field, and then they deposit onto the cathode, in which we have our fabric is backed by the electrode. But what's interesting about this process is that, and we recently patented this process because it gives you an extremely uniform coating on all of the fibers in the bundle. And what you can see here, it's a sponge-like porous nanocomposite coating. And this kind of it's soft to the touch, it's breathable, but it gives us this nerve-like sensing functionality. So these are just some examples where we've applied it to different types of fibers. On the left is a nylon fiber, on the right is a wool fiber. And what you can see is the wool has this scale-like or cuticle-like structure, and that coating is very thin, just a few hundred nanometers thick, and it uniformly covers the entire fiber. And what's unique about this is we can use it in a wide range of sensing applications. And in this case, this was an Embry-supported program, and my collaborator was my friend and colleague Jill Higginson. And her area of expertise is gait analysis. And with these types of sensors, you can really take and monitor people in everyday settings, over different terrain, looking at the kinetics and kinematics of walking. And this is actually the video you see on the right. This is Ian. He's one of the undergrads who was supported on the project, and that's kind of the first generation of our sensor. And this sensor is quite unique in that it's very thin, it's flexible. In this case, we're using it as a pressure sensor, and it has an extremely wide dynamic range. So here you can see on the left the photo. That's me actually putting it in the sole of the shoe I'm wearing right now. You see that, so it's a very thin layer, and we can put it both in the ball and the heel of the foot as well. And to the right hand side, you see the hind foot and the forefoot. So those are the reaction forces. But typically, if you're on an instrumented treadmill, you get the curve on the right-hand side. That is the black curve. So we're able to separate those out. And we can also look at people walking over different terrain. And as I mentioned, this has extremely wide sensing range. So we talk about it being from touch to tons. It's sensitive to just the low forces of tapping on it with your finger. Of course, in the middle, you see body weight, and we ran over it with the forklift in the manufacturing lab, so several thousand pounds. So it's a remarkably durable and repeatable sensor. And so this is some new results where we've done human subject testing where we calibrate this, and we have people come in and we have a bunch of different shoes that are instrumented. And this is just an example showing the validation of the sensor with the treadmill response. So we calibrate the curve. We have the human subjects come in and we calibrate it. And then they go and walk on the treadmill at different rates. And you can see that the results are quite nice. And that gives us the opportunity now that we don't have to just do this in a treadmill, but we can walk around wherever you want to go. And so on the left, that's the reaction forces. If you're walking up the stairs, you put more weight on the front of your foot. The right is just the walking on flat ground. We have data on all kinds of different surfaces. So those are the pressure sensors. I think another is that not only do we want to look at the kinematics, but also the kinetics of walking. And here we have an elbow sleeve and also knee sleeves where we've integrated these novel sensors. And what you see is this extraordinarily high sensitivity actually is that, near mid-flex at about 90 degrees, that sensor changes over 3,000% resistance. And even at just a few degrees, you're looking at also a very high change in the electrical resistance. The video on the right shows the real-time response to the sensor. And so this is, where you have these textile sensors that are actually integrated into a compression garment on the legs. And this is just an example of sitting and standing. Again, similar type of response that we see on the elbow. And it's also extremely sensitive to just these very small motions. So on the right-hand side, the video you can see is that is Sagar, who's a PhD student working on the project. And you can see just that, clenching a fist, just that very slight muscle movement, the sensor is able to pick that up. On the left-hand side, that's where we have a finger sleeve, and he's gripping different diameter, things in the lab. And again, you see this very sensitive to these very small motions in so we could have like a smart glove or something like that as well. This is one of the more recent things is that, we want to be able to analyze motion. So this is just a video of, and you can see in the lower right-hand corner, one thing that we've added and really upgraded recently is our capability to make really small scale electronics. So we can print our own circuit boards. And what that is right now it's completely wireless and it's communicating to the laptop that's in the background using Bluetooth. And so we're able to, this is just kind of the first step of playing around with being able to map this. So I guess with that, I'd certainly like to acknowledge all the people who have worked on this, especially Sagar Doshi. He is a PhD student who will be defending very soon. Jill Higginson I worked closely with in the gate analysis work, and Andrew Ryder, who I spent my sabbatical in Australia. We worked closely on the coding process of electrophoretic deposition. And there are a couple of more recent things from the last time that I talked is that about 8 months ago, we received early stage startup funding from the Unidata Foundation to start a company to commercialize these sensors. And recently we also won the DuPont Fast Pass. And so we actually are up near Nemours. So we have space in the Delaware Innovation Space. And we actually just moved in earlier this month. And so the company is called MSET Technologies, and it stands for Multifunctional Composites and Engineered Textiles. It also happens to be my old school rap name. But so that's the DuPont Fast Pass. We have a nice little, they call them lab pods. They're about 10 feet wide, 15 feet deep. And that's the lab pod. The first visitors were my parents, so that's them in the picture. And actually somewhat related to the sensing technology, we have also recently, this is the Walnut Street Bridge near the train station in Wilmington, and we have a sensor mounted on that. So with that, I'd be happy to take any questions.